Hello, Calculus. I'm going to do this so-called Chapter 10 review. So-called, well, it is called that, um, but I would stop way short of telling you that this was some kind of comprehensive review of everything in Chapter 10. I think this hits some of the key things that we need to know, but I would definitely encourage you to go back through the different kinds of problems that we did. You could check your notes for topics, and then if there are things that you think you need to practice a little bit, then find some practice problems and do them. Okay, so here are some examples of some things. In my experience, we get so deep into all the series business that we tend to forget about sequences and what is like the language, what are the things that we say about sequences. So which of the following sequences converge? This is that curly bracket notation, you know, that should remind you that you're just talking about a list of numbers here. So which of the following sequences converge? That's just about like what are these things approaching. They don't have to be approaching zero. We're not talking about a series and adding stuff up. We're just talking about a list of numbers. Is the list getting closer and closer to something as you go out further in the list? This one is going to go to approach zero because it's got a higher power on the bottom. This one is going to approach 2 because same power top and bottom. If you're like, oh wait, that's not 0, so there's no chance. This is not a series. We're just talking about a sequence converging. And then this would actually be a geometric sequence, and since the r is bigger than 1, the r is 1.2, right? You're multiplying by 1.2 more and more times here. Since that's bigger than 1, that's going to blow up and go to infinity. So that does not converge. So which of the following converge? Let's say the first one and the second one. Find the sum of this series. If you are actually going to find the sum of a series, there's only two possible ways you can do that. One of them, this is a little bit less common, we'll take a look at this later, would be to match up your series to, like the actual numbers you have, to a series that you know, like the series for the sine function or cosine or whatever. And the other way, much more common, would be to have a geometric series, because that's the kind that we know. We know how to find the sum of a geometric series. It's the first term over 1 minus r if the multiplier is between -1 and 1. So here my first term is 3, and it looks like I'm multiplying by -1/2 each time. That's a sign mistake waiting to happen. Please be careful. And that's going to be 3 over 3/2. Dividing by a fraction, same as multiplying by its reciprocal. So that series converges to 2. All right. Write out the first 4 non-zero terms of the Maclaurin series and give the interval of convergence. So these problems are about well, let's take a step back and think about what are the different ways that you know to write a series. Of course, there's the from scratch method where you actually find all the derivatives and then use the recipe for a series. That always works, but there are shortcuts. And here, for example, use the definition of a Maclaurin series. This is suggesting to us or instructing us to use that recipe for making a series. But here it doesn't say that. So if I know my big 4 series, if I know the series for sine, cosine, e to the x, the like geometric series type, things that are the form of first term over 1 minus multiplier. Those are easy to write. And then the other ones, if you've got a little extra room in your Taylor series memory bank, you could also look at the natural log of 1 plus x and tangent inverse of x are 2 series that also come up. with some regularity. But the big four that you for sure would want to know are what are the series for sine, cosine, e to the x, and things that are like 1 over 1 minus x, right, where you can just kind of replace those things, like that one. Okay, so what are the first four terms here? The first four terms here are, well, I know that the cosine series, I'm just going to write that out real quick to make sure that we know that, is cosine is even, so this is all like the even powers. And I'll dot, dot, dot from there since I need the first four. And the interval of convergence for sine, cosine, and e to the x, those are ones that converge everywhere. Factorials on the bottom is a strong indication that you're going to get that convergence everywhere. So here, if I want to do cosine of 3x, I just have to replace all the x's in this with 3x. So that's going to be cosine of 3x is equal to 1 minus, you want to simplify these, you can go for it, but I'm not going to because I got better things to do. No, come on, that was, if you're thinking to yourself, no you don't, Mr. McGrath, I do have better things to do, I promise you. That's mean. So there's the first four terms. Now cosine converges everywhere, so that's where like x, you could think of it as being like x from, we don't write it this way, we just say that it converges everywhere. So since I'm replacing x with 3x, I can do the same thing for the interval of convergence, and of course that means if 3x has to be between negative infinity and infinity, that still converges everywhere. All right. For this second one here, I know that the series for 1 over 1 minus x is equal to, that's a geometric series where the first term is 1 and the multiplier is x, and so on. So this is like a geometric series with a first term of this, right, a sub 1 over 1 minus r. So the first term is 5x squared, and the multiplier, this is 1 plus x, and the geometric series formula is, oh, there it is, right there. So the multiplier is minus x. So that's going to look like that, right? There's the first term. The multiplier is a minus x. And what would the interval of convergence be? Well, for a regular geometric series, the multiplier, the r, has to be in between -1 and 1, and that's also true here. So that means that x, or in this case, minus x, has to be between -1 and 1. And then if you just kind of rearrange that, then clearly that also means that x needs to be between -1 and 1. Do you have to check the endpoints? Think about that for a second. Pause the video. Think about that for a second. Now, the answer to that question, do you have to check the endpoints, is no, because this is a geometric series, and geometric series never converge when the multiplier is 1 or -1. So you do not have to check those endpoints if it's geometric. All right. Now this one, I know, maybe you know, or maybe you should know, that the series for the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3, and so on. So that means the series for this is going to be Oh, that's not actually properly a series, though, is it? Um, hmm. So for this one, I guess maybe we would have to do this is why. Let me just pause for a second here, make sure that you're following my thought process. I could, if you're thinking, well, can't you just like replace all these x's with x to the 1/3? You could do that, except for the fact that you're going to get, these are not like whole number powers, and that's not a power series, right? A power series is a polynomial. These things are like tangent lines, quadratics, cubics, and so on. We're not allowed to have fraction powers in there. So that means I would actually have to find natural log, this is my f of x, 1 plus x to the 1/3. And we're doing this, we're finding the series for this at x equals 0. So I'm going to have to find the first 4 derivatives of this, or first 3 derivatives, to get those first 4 terms. That looks like it's not going to be super pretty. So the here, the derivative of natural log of whatever is 1 over whatever times the derivative of what's inside. And then second derivative, maybe I'll go as far as this. I don't know if I want to take another derivative after that. I'm going to have to use the quotient rule for this. So that's low d high minus high d low all over low low. And at this point, sorry I asked you to do 4 terms. I don't think I'm going to do that, because that would just be horrendous. But it shouldn't be too bad when we just have to plug 0 into this. So let's see. When I plug 0 into this here, I get natural log of 1, which is 0. When I plug 0 in here, I get I get trouble, don't I? I think that this is a poorly formed problem. Why can I not make this series? I guess because, let's just take a look at that. We might have to chuck this one out the window, folks. That's okay. It's a learning experience for all of us. To the 1/3. And what kind of window I got here? I think I would like to see. Now we're trying to make the series at x equals 0, so I'd like to look at it in a window around that and see what's going on. So this must have some kind of issues. Yeah. So the problem with this thing is it's not differentiable at x equals 0. So if you're going to find the Taylor series or the Maclaurin series, in other words, the Taylor series at x equals 0, you need to be able to find the derivatives at x equals 0. So this is a bust, because I think all of the derivatives do not exist, not differentiable. So this is a bust. Sorry about that. Use the definition of Maclaurin series to write out the first three non-zero terms of the series for sine squared x. Now you can do that doing the little multiplication table thing. You could do this game. Say, well, I know that series, so I could just, sine squared is just that series times itself, right? But the directions here, which we are going to respect, say use the definition of the series. So that's like this game. So let's see, if my f of x is sine squared x, that's better calculus notation for us. Then the first derivative is 2, derivative of something squared is 2 times that something times the derivative of what's inside. And then the second derivative is, there's two ways you could go here. You may recognize that this is the sine double angle. So if you want to turn this into sine of 2x, that actually makes the derivative taking easier. But if you didn't recognize that, you can just use the product rule. And that's going to be 2, I'll take 2x to be like the first. Derivative of the first times the second plus the first times the derivative of the second. And is that, I want the first three non-zero terms. So let's see what I get here. If all three of these are not equal to 0, then I'm going to be okay. But I think that we're not going to be okay because f of 0, that's 0. So that's going to give me not a term there. And this is also 0. Oh, that's no good. And the second derivative is the first place where I get f prime of 0 is equal to 2. Right? That's 0, and cosine of 0 is 1. And then this is where it's super helpful to recognize that that is the sine double angle, because then that would have given you, for the second derivative, what's the derivative of sine of 2x? It's 2, because of the chain rule, cosine of 2x. So maybe you recognized here the cosine double angle formula, right? 2 times cosine squared minus sine squared. And then the derivative taking is way easier. Now it's just minus 4 sine of 2x. And then the fourth derivative is minus 8 cosine of 2x. And we should check in here and see what's happening. That's a sine of 0. That's going to give me another 0 there. And then the fourth derivative is going to be negative 8.
Mr. Flashman, I have a phone call to put through to your office.
And then here, derivative of cosine is negative sine, so it's going to be 16 cosine, oops, just kidding, 16 sine of 2x. That's going to be 0 again. And then finally, the sixth derivative gives me, derivative sine is cosine 32 cosine of 2x. Cosine of 0 is 1, so the sixth derivative at 0 is 32. Okay, so I got those, and I know that the recipe for a series is the f of 0. Why did I write an equal sign there? That was weird. F of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and yada yada yada. So my first term, or my 0 degree term, is gone. That's gone. The first thing I have is my second degree term. So f double prime over 2 factorial times x squared. when I get down to this one, that's going to be f quadruple prime, which is minus, I'll write it like this, minus 8 over, that's the 4, so 4 factorial times x to the 4th plus 32 over 6 factorial times x to the 6th. That's the first 3 non-zero terms right there, done in that way. This would have been easier, but we have different ways of doing these things. All right. I wonder, could you write out the general term for that? Want to add that to this problem? Why don't you pause the video and see if you can figure out how to write the general term for this. The general term is going to be, are you still here? Pause the video. Even numbers factorial. So if I start with 1, that gives me this. And then this is 2 to the 1st, this is 2 to the 3rd, this is 2 to the 5th. So this is the odd numbers that are 1 less than these. So that's 2 to the 2n minus 1. And then there's also a sign flipper that if you start with 1 here, which I would like to be able to do, I want that one to be positive. So that is the general term. Oh, times, forgot my x's. X to the same number as that. That's my general term. Okay, find the interval of convergence for each of the following series. So how do I find the interval of convergence of something? I do the ratio test. So for 5a, I'm going to announce to the world, hey world, doing the ratio test here. So I'm looking for the limit as n approaches infinity of the n plus 1 term divided by the n term. It's divided by this. Dividing by a fraction is the same as multiplying by its reciprocal. Okay, now when I simplify this, this n approaches infinity doesn't have anything to do with x's, so remember that x stuff can come to the outside. There's one more x minus 3 on the top than there is on the bottom. So x minus 3. And then on the inside I have limit as n approaches infinity of 2 to the n over 2 to the n plus 1. That's 1 extra 2 on the bottom. And all the n's actually cancel out. So what's the limit as n approaches infinity of 1/2? It's just 1/2. What is that telling us? If you're thinking to yourself, that's kind of weird. What that's telling us is the limit, remember that the ratio test is about comparing things, comparing a series to a geometric series and trying to figure out, does the series behave more and more like a geometric series as you go on and on? And what this is telling us is, hey, dummy, it actually is a geometric series, and the multiplier isn't getting closer and closer to 1/2. The multiplier actually is 1/2. That's what this is telling us. So that's fine. That means we just have this, and then when you get this far in the ratio test, that's the thing, whatever shows up here, that has to be in between -1 and 1. So and algebra happens, so that's -2 to 2, and then I add 3, so it looks like my interval is going to be that, right, after we do the algebra, and then I have to check the endpoints. The endpoints are 1 and 5. So at x equals 1, when I plug x equals 1 into this, I get negative 2 to the n over 2 to the n, which is going to be, when I plug in 0, I'm going to get 1, and then I'm going to get negative 1, I'm going to get 1, I'm going to get negative 1. So that is a bust. It does not converge there. And then here, when I try 5, well, that's even worse. Well, whatever. If you're thinking to yourself, well, doesn't that converge to 0? No, it does not. The series of partial sums, if you add up the first two terms, well, if you add up the first one term, it's 1, and then it's 0, and then it's 1, and then it's 0. And by definition, a series to converge, the partial sums have to approach something. They can't be ticking back and forth like that. So also know, so this is the interval of convergence. And in retrospect, when we notice that this was a geometric series never converge at the endpoints. You could probably say that here instead of checking the endpoints, but I don't know. I'll just check the endpoints every time. All right, ratio test here 5b. When I do the ratio test, I do not do the, I guess I'll at least stick with the k here, right, since it's k's in this problem, doesn't matter. We throw out the sign alternator just for the purposes of the ratio test. So I have x to the k plus 1 over k plus 1 factorial divided by that term the x's can come to the outside. There's a 1 more on the top than there is on the bottom. And that's going to be 1 over k plus 1. And the limit as k approaches infinity, 1 over k plus 1 is 0. So that converges everywhere, because no matter what x is, it's always going to be, this is always going to be in between negative 1 and 1. So we're good. So you have to check the endpoints? Nope, those aren't really endpoints, right? There are no endpoints. It converges everywhere. Not too surprising there, because I had a factorial on the bottom, right? All right. What else we got here? Here, this looks like a College Board free response question. It is. Write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 0. Well, that is that's just e to the x with negative x squared plugged into it. So if I know that e to the x is equal to 1 plus x squared over 2 factorial. And you should know these. You need to know these big four. Sine, cosine, e to the x, and geometric series type. So if I know that that is true, then e to the negative x squared is equal to 1 minus x squared plus negative x squared squared is x to the 4th. Negative x squared cubed is minus x to the 6th. And so on. Did they want the general term also? Yes. So the general term here is, well, if I know the general term of this is just x to the n over n factorial. Then here, the general term here must be negative x squared to the n over n factorial. Right? Then you don't have to worry about the figuring out the evens and what's going on there. Just take that general term and do what you did here. Plug in negative x squared in place of the x. All right, so that's part A done. Part B, use your answer to part A to find this. Okay, so when you see this kind of thing in a series question, you got to think about like some of the terms are going to cancel out here, right? So if I'm looking for the limit as x approaches 0, this I've got 1 minus x squared minus 1 minus x squared plus x to the 4th. This is f of x, right? And I know this is my series for f of x. So I can throw that in there. And hopefully that's enough to see what's going on. So 1 minus x squared plus x squared, those cancel out. So the first non-zero term that I have is this one, this x to the 4th, and there's a minus sign out here. Don't make that sign mistake. Minus, minus. And then you can see what's going to happen here. The x to the 4th, if you knock down, if you divide x to the 4th out of all these, that's still going to be x squared, and all of the rest of the terms of this are still going to have x's, which will go away. But this one, all the x's cancel, and I just get negative 1/2. Right. Write the first 4 non-zero terms for the Taylor series. This about x equals 0. So that's the antiderivative of this. Okay? So that's going to be, antiderivative here is x. Antiderivative of this is minus x cubed over 3 plus x to the 5th over 5 times 2 factorial. I'm not going to simplify. Why would you bother? Minus where? Oops. Sorry. X to the 7th over 7 times 3 factorial. And that's what they wanted, right? Yes. Use the first 2 terms of your answer to estimate this. So the first 2 terms, plugging in 1/2, you get 1/2 minus 1/2 cubed over 3. You want to simplify that? Go ahead. But telling you, there's no payoff for doing that. Just in case you simplified it and you want the satisfaction of knowing that you are correct, this is 1/8 divided by 3 is 1/24. That's 12/24, so that's 11 over 24 if you simplified it. Not recommended. And then part D, explain why the estimate differs, so talking about error bound, why the estimate differs from the actual value by less than 1 over 200. Well, this is an alternating series, so I can use the alternating series error bound, which means that my approximation that I got from using the first 2 terms, the difference between that and the actual value of this, how am I going to represent that actual value? I'm just going to write that actual thing. The difference between the estimate and the actual thing must be less than the next term, absolute value of next term, which is this with a 1/2 plugged in. Oops, sorry, this with a 1/2 plugged in. We're talking about this series here. So that's and probably in here, if I want to really be good about this and make sure I get all the points, I should say because the series is alternating. And the terms are approaching 0, then I can do this, alternating series error bound. Now, same thing, if you want to simplify this, you can. That's that's like 300 and something. But whatever this is, it's definitely less than 1 over 200. Do you have to simplify this to prove to the world that it's less than 1 over 200? No, you do not. Just have to have the right stuff there. All right. Find the exact value of the series in number 5b at x equals 2. So finding the exact value of a series, it's either got to be geometric or we've got to recognize what it is. So let's see. 5b. Where's my work for 5b? Here it is. At x equals, actually, I don't need the work for 5. I just need what the series is. So we could either recognize what this is. Let's write out some terms of this and see what's up. So this is k equals 1 here. So the first term would be negative x. And then the second term, when I plug in 2, it's going to alternate. Then I get x squared over 2 factorial minus x cubed over 3 factorial plus, and so on. And if you're looking at this and you're thinking, that's kind of like the series for e to the x. Could I take the series for e to the x and turn it into this? This is my target here, right? Because that's the series I actually have. So e to the x is equal to 1 plus x plus x squared over 2 factorial and so on. And then e to the negative x, if I plugged in negative x, then that would give me 1 minus x. That would get it to alternate. Right? And that looks just like this, except for that 1 at the start. So how do I get rid of that? Well, you just subtract 1. So e to the negative x minus 1 would be equal to this. I'm just subtracting 1 from both sides. And that is the series that I actually have here in 5b. So what is the exact value of this series here at x equals 2? It is e to the negative 2 minus 1. Right? So that's tricky, I think. Not going to see a whole lot of that from the College Board, but I think it's important to realize that we can, with all of this, like, oh, it converges. What does it converge to? I don't know. I just know that it converges. Like, every once in a while, if we get lucky and we can match the series up to something that we know, like sine, cosine, e to the x, or geometric series, then we can actually report what it converges to.